I am looking forward and excited to share with you that our next speaker is one of the speakers I'm personally excited about. She is an amazing security professional. She's actually not just a security professional, she's a team lead. She leads security research for Windows Defender Advanced Threat Protection at Microsoft. Now, I have to share with you a secret about our next speaker. Her name is Dana Baril. Dana was here in Israel during the pandemic, but she got called by Microsoft to Seattle. So she's joining us from the West Coast. So this next talk may not be as live as we would all like it to be. She's not right here on the stage, but we're extremely thankful for her for joining us at this early hour of 4 in the morning, I think, or something around that time, all the way in the West Coast. So Dana's going to be talking to us about eliminating alert fatigue, a fantastic topic for an after-lunch coffee break session. Grab a coffee, because this is going to be a fast, fun talk about eliminating alert fatigue and how to do better as a security professional. So Dana started her career in the famous 8200 unit. I know you know what I'm talking about. Wink, wink, say no more. And she's also worked for Google in their security team in Zurich, Switzerland. Dana is very passionate about operating systems and Windows internals. And in her spare time, she also volunteers with high school students, mentoring the next generation of cybersecurity experts. I first met Dana through the Black Hoodie Initiative, which is a reverse engineering seminar for women. First started in Vienna, but now it's become a global phenomenon. And Dana was working super hard to actually bring Black Hoodie to Israel this summer. It didn't work out because of the pandemic, but sign me up for next year. So I hope you're ready for this amazing talk about eliminating alert fatigue. Please welcome, give her a round of applause, even though she's not here in the room, Dana Baril. Thank you, Dana.
Hi, everyone. Thanks for joining my talk about reducing alert fatigue through better engineering. I am super excited to share with you some of the work we have done over the past 2 years. Before we start, let me introduce myself. My name is Dana. I am the Security Research Lead for Windows Defender ATP. I am originally from Israel and currently based in Seattle, Washington, in the Microsoft headquarters. I work on fascinating research projects and had the opportunity to present some of my research in conferences like Black Hat and Blue Hat. And I love dogs. So let's talk about dogs for a second. I don't know about you, but my dog is a barker. When I got her, I would be alerted every time she barked. But now, I learned to ignore the barking as I realize most of it is false alerts. What I experience is alert fatigue. I am tired of wasting my time investigating my dog's alerts. This is exactly what happens to SOC teams hunting for threats. If they get too many false alerts, they experience the same alert fatigue that we would like to avoid as security vendors. You are probably thinking, so why do we produce FP in the first place? There is a number of reasons for that. First, we need to remember that most software and environments that we use are dynamic. We install new software and we update existing software. In many cases, these contain API misusage. The benign software uses APIs in ways that may seem suspicious. Another reason for producing FP alerts is data gaps. Sometimes the security provider doesn't have the required data to determine if an activity is malicious or not. When that happens, some will generate an alert out of conservatism. One more reason for FP is false detection logic. This could be related to a lack of testing, flawed assumptions, or other human mistakes. I'll talk more about how we can minimize this, but I should mention that the first two reasons are the core sources of FPs, and fortunately, the human factor is normally insignificant. The last reason has to do with alerts misinterpretation. When a TP alert is identified as an FP alert. As part of the work I'm presenting today, we made some product improvements to address this. However, this is beyond the scope of this engineering discussion. All right, so we understand the root cause for FPs. Let's tackle this. The traditional approach to producing security alerts is to cover as many TPs as possible with the minimal amount of FPs. As the diagram shows, we set the threshold based on the context, balancing FNs and FPs. Highly sensitive environments will lean conservative to ensure they don't skip any TP. Generally, you want to cover most cases, introduce the least number of FNs while avoiding FPs. This should be the approach when introducing a new detection algorithm. However, this approach introduces a trade-off between FNs and FPs. We were looking to shift the curve, eliminating FNs without compromising FPs through better engineering. In order to do this, we need to leverage data to drive engineering improvements. Data that helps us understand FP generation, focusing on alert conclusion data. We leverage data from three different sources. First, we use customer feedback. For each alert we produce, we ask customers to provide us feedback. While we don't always receive feedback, it helps draw our attention to pain points. Next, we leverage expert graders. That's our in-house experts that verify alert accuracy. Initially, they graded alerts randomly. However, in order to optimize their productivity, we developed contextual clustering. So instead of working through alerts randomly, they grade related alerts in bulk to save plenty of overhead. These two manual sources are great, but not enough. In order to understand our detection precision rate, we need to scale our testing. For that reason, we introduced a machine learning model to predict alert conclusions, leveraging our manual inputs and scaling their impact. This tool predicts individual alert conclusion using multiple machine learning models to achieve high confidence alert grades. So let's take a moment to understand where we are. We understand why we have FPs and the trade-off that involves reducing them. We can leverage alert conclusion data to transform this trade-off. So let's examine how. We started by analyzing the alert generation process, breaking it down into its components to identify FP root cause. I like to refer to this process as a loop, producing new alerts that are being assessed, then being monitored to identify pinpoints to fix. Breaking the loop into steps helped us to focus our attention on the most vulnerable components to ensure our efforts move the needle. As part of this, we analyze the process step by step to identify which kind of FP can be avoided in each component. This included better engineering guardrails and reiterating engineering guidelines. In addition, we started to measure FP fixing time in order to minimize it. We then tackled the alert fixing process, introducing new tools that I will cover in the next slide. These tools enabled us to discover FP cases faster and solve them quickly. So even if we produce unwanted FP, the fixing cycle will be closed first without customer reporting and before customers even notice it in most cases. For example, we introduced a new component into the alert generation process. That's the FP filter. This filter combines rule-based logic and machine learning models to address FP in real time before they become customer-facing. The rule-based filtering enables us to apply broad filtering for common FPs patterns across different types of alerts. The machine learning model predicts FP based on prior conclusions and other contextual features. If the FP filter makes a definitive judgment on a specific pattern, we will circle this insight back into our detection logic. However, this component is intended to pick up on unpredictable behaviors that cannot be programmed into the detection logic. Last, I previously mentioned auto-grading tool, which is another addition to the alert generation process that enhances our detection capabilities. The auto-graders, the auto-grades are fed into this flow, supporting the precision assessment and the detection fixing and of course, the FP filtering. The next step to reduce FP through better engineering is to introduce new tools. The first tool we developed is a proactive anomaly detection tool that monitors alerts production in real time and flag suspect FP based on observed anomalies such as volume spikes. This tool notifies us when it detects cross-customers anomalies. These are phenomena that impact multiple customers, making a breach less likely. This notification will trigger an internal flow of urgent fixing to address this case. We also introduced an alert clustering system, which clusters alerts based on features similarity, and then delivers a conclusion for each cluster. This way, we get an overview of alert patterns and we can tackle them at scale, providing a conclusion such as TP or FP for each pattern. This allows us to review the alert patterns and their conclusion automatically and reduce time to fix. To summarize, as part of our engineering efforts to minimize FP cases, we first analyzed the overall alert generation process for improvements. In addition, we introduced a new FP filtering component to filter FPs in real time. Next, we developed the automatic grading mechanism to grade alerts at scale for better conclusions. Then created the alert anomaly monitoring to detect FP cases in real time so we can tackle them quickly. Last is our alert clustering approach, which was introduced multiple times as part of alert grading and as a post-alert FP analysis. Our main takeaways from this process are, first, clustering increases our productivity so that instead of reviewing FP case by case, we can cluster similarities, review alerts in bulk, and tackle them at scale. Second, by breaking down processes, we can better engineer a solution. It allows us to analyze steps along the chain, determine which ones can be automated, and of course, scale human impact, empowering researchers. Next, like the old-fashioned engineering approach, we should always start small with a POC, prove its value, and then scale. Everything I presented today started from a POC. Last, in order to produce meaningful results that move the needle, we must identify which key levers we need to optimize for. We optimize for time to discover, time to fix, and detection precision to keep our eyes on the ball.